So we're going to do this problem, and this problem includes an interesting aspect to it that isn't necessarily in all the problems, and it's that a lot of the geometry in this problem is given with coordinates rather than things that look like they are measured right on the figure. And so that's kind of the different thing about this problem. It's not actually that difficult, but it may look a little bit intimidating whenever you first look at it. So basically the idea here is that this represents a set of alligator jaws, and in the process of alligator jaws closing on a snack, such as the one shown there, it applies some force to that snack, and we know that force. It's 130 pounds, and what we want to do is figure out how much force has to pull between points B and C on this figure in order to produce that amount of force on the snack at point A. Okay, so this is the task that we have before us. How would you like to begin? Yeah, you guys know the answer. Free body diagram. Okay, that's right. So what do we draw a free body diagram of? Okay. The jaws is one answer. It's what someone suggests. That may not be all that helpful, given the fact that one of the things that we need to know is a force that acts between the two jaws, right? Okay, you could look at the snack itself. Okay, the downside of looking at the snack itself is that there are no direct forces from the muscles that we're supposed to be trying to find the force in. Those are not directly applied to the snack, and so those variables probably won't show up at all. Okay, any other suggestions? Say what? Yeah.
What about the moment around point D that was...
Okay, the moment around point D. So what we're doing is we're skipping over and thinking about what equation might we write, and that can be helpful, but that should help us inform us what free body diagram we should draw, because we don't write equations till we have a free body diagram. So I like that idea, but what free body diagram do we need? Okay, point D, again, point D actually might not be enough because there is no force applied directly from the muscles that we're supposed to be trying to find the force in applied to point D. Okay, so we don't really want to just do point D. You got another thought? Okay, we want at least one of points B and C to show up in this equation, because if you think about this, if we were to actually draw those muscles would basically be like another member, so to speak, another piece that would be connecting between B and C. That's the member in which we would like to find the force, right? So we need to at least have a body that member connects to, at least one body that it connects to. Okay? I haven't heard anyone kind of come up with what I think is the best thing to use as a free body. Yeah? Okay, we could do one for each jaw, and I tell you what, let's start with one of the jaws, and we'll see if we even need both of the jaws. Okay? So let's start with the lower jaw. All right? And one thing that I'll point out here is whenever you're drawing these free body diagrams, it isn't always perfectly necessary that you draw the figure exactly what it looks like in the given stuff. What you need is all of the geometry that matters to you. You need that geometry to be accurately represented. You don't necessarily need the whole detail of the whole thing. So what's the geometry that matters to us in this problem? So like we would want to know probably what's going on at point A. There's a connection, there's a rigid body that connects from point A to point C, right? And then there's also that same rigid body goes up here to point D, right? And there's sort of a hinge action that happens at point D. So what I'm going to do is take that little figure right there and draw that as my free body diagram. Okay, a line like this and a line like this. That's my free body diagram. Okay, but that's at least my free body, my body that I have now freed. Okay, what else do I need to add to my free body diagram? Okay. I might need to do some coordinates at some point. I do need forces, so let's start at point D. Okay, it even says in here, it says it hinges around point D. That a hinge is just another way of expressing the same idea as a pin. All right, and what kind of reactions would you see at a pin? Okay. It's not allowed to translate relative to the other part that it's connecting to. It's not allowed to translate left and right. It's not allowed to translate up and down. And so what that tells us is that we should have reaction forces shown there at D. So let me name those RD in the X direction, RD in the Y direction. And there I've begun to imply, of course I already had my X and Y shown on here, but let me show these again over here. Here's my X and here's my Y. Okay, what else? Okay, there is a force at A. Do we know anything about the force at A? Okay, we know its magnitude is 130 pounds. Okay, so that's good. We can show on this diagram the amount of magnitude of force. What else do we know about it? Okay, it is perpendicular to a line between A and D. So what that tells me is that if I draw a line here that goes straight from here to there, right, the direction of the force that acts at point A is along a line that's perpendicular to that line. Okay, what direction would you like to show the force at A? Okay, we know first of all that its line of action is going to be perpendicular here, so that much we've established. But what we need to do is we need to decide if we want to show the arrow pointing down and to the right or the arrow shown pointing up and to the left. Okay, I hear one vote that says let's show it pointing up and to the left. Who agrees that that might be a good place to show it? It doesn't super duper matter. Okay, so I'm okay with that. We'll go ahead and stick it on there pointing up and to the left. Okay, but what I want to do is I want to physically interpret that. Okay, let's physically interpret what that arrow means. Okay, any thoughts? What does that mean? Because what we're doing right now is showing all the forces applied to jaw AD or ACD. Okay, so what does that mean the snack is doing to the jaw at that point? Okay, if you saw this from the standpoint of the snack, right, here's the snack over here, you would say that the jaw is applying a force like this to the snack based on Newton's third law. What does that mean? Okay, so let me interpret this for you. What you're saying is that the snack is pulling on the jaw up and to the left, and you're saying that the jaw is pulling on the snack down and to the right. That's possible, I guess, if the snack is like bubble gum or something like that, and it's really, really sticky, so that you're trying to open the jaws and they won't open because the snack is sticking to the tooth.
Also, since they're trying to find the force of the muscles, the jaw is like a lever, so the force of the muscles are going to be down like that.
Okay. So we're going to get there too. So his comment was there's also the force in the muscles that we need to consider, and so we'll kind of have a similar discussion there. I tell you what, I don't actually love the direction that force is going right now, even though someone made a correct comment and said it doesn't really super duper matter, right? It doesn't, but at the same time, since we can look at this and fairly easily see that that's kind of a ridiculous thing to happen, I'm going to go ahead and show this like this, showing that the snack is putting a force in that direction on the jaw. Okay? And we said a second ago we knew the magnitude of it. What was it? Okay. 130 pounds, and I'll go ahead and do this as well and indicate that that is perpendicular to that line. All right? Now what? Okay, we have another force that we need to deal with at point C. Okay, Now, some of you are probably familiar with how muscles work. Muscles don't really do a good job of applying compressive force to things, right? Muscles are basically tensile members. They're like ropes or something, right? But they have the ability to change in length. So they have the ability to contract, and as they do that, they can put large amounts of force on the bones they connect to, but they don't really have the ability to elongate and push on the bones they connect to. They can really only pull, right? So that's the direction that we probably want to show the force in the muscle acting on point C for this jaw. If I'm assuming that there is a tensile force in muscle BC, which I have shown up there with a little green line, what direction of the force would I need to show on the jaw? Okay. So I think someone says opposite direction of what you would see in the muscle. So here, if this is the muscle, that's kind of a little miniature free body diagram of the muscle. If it has tension in it, what that means is that you are applying a force that tries to elongate it, right? Or it is trying to contract and pull together, right? This would be an assumption of tension. This is the type of force that would be tension in that muscle. So if that is tension in the muscle, what direction of force would I have applied at point C? Remember, this is point B, this is point C. So what force should I show applied at point C? Okay, let me write those up here as well. This is A, this is C, and this is D. Okay, Newton's third law says the direction that I imply the force is at location C is going to be up and to the left. Okay. Should I assume that that direction of that force is perpendicular to that dotted line between A and D that I drew a second ago? Okay. While it might be tempting, what's the problem with doing it that way? Yeah, so, I mean, I think he says math doesn't work that way. You know, really geometry, that type of math, it doesn't work that way because I know the coordinates of point C and point D, right? So I already know the line of action, of force that should exist in that muscle that goes between B and C since it acts in a pure tension type of a way. You know, it really acts just like a rope or a link even. And it has to, we know the direction of the line of action of the force that exists in that member. All right? Do I know the magnitude of that force? Okay. I do not, so what do you want to name it? Maybe F, B, C? Okay. And that is the value that we are trying to find. It says the force that the jaw muscles must exert to achieve the force A is closest to, right? That is what we're seeking. Okay. So this is so far pretty good for a free body diagram. What are we missing? Okay. We're probably missing some lengths of things, right? Like what? What kinds of lengths would matter to us? Okay. Yeah, I actually agree. Someone says the length from A to D. All right. That is a length that would be very helpful to us. So I'll tell you what I'll do. Let me just show that on here real quick. This is the length that someone is mentioning we might want to get, right? A length that goes directly from A to D. Why do you think that that might be a helpful length? Okay. Yeah. I think most of you are looking ahead and saying, at some point, I want to some moments around point D for this body. Because if you can some moments around point D, what does that do for you? Right. So someone says you can cancel out the reaction forces at D if you sum moments around D. And since we don't care about what those are for what the question is asking, this is a very helpful equation for us to write, and so we want to be able to do that. Okay? So what is that length right there? Maybe I'll just LAD. Okay, we can do a little bit of distance formula, right? And what you see there, since A is at the origin, right? this value right here, A is at the origin, all you have to do is look at the coordinates of point D, and you will see that we just need 21.3 inches squared plus 7.1 inches squared. Right? Beautiful. Okay, so let's do that real quick. All right, 21.3 squared plus 7.1 squared. Oops. Okay, and that length is approximately 22.45 inches. Okay, so I'll put that right here, 22.45 inches. Okay, what else might be helpful? Okay, how far is it from C to D? Although I tell you what I think is going to be more helpful than that direct length. I want to know the components of length in the X direction and in the Y direction to go from C to D. Okay, why is that important, you think? Okay, yeah, I'm going to need to split FBC into two components in order to figure out the overall moment that is created around point D there. Okay, so what I need to do there is do that and also come up with how far is it both horizontally and vertically to go from C to D. Okay, so maybe I'll say LCD X, right? LCD X. What is that? Okay. Okay, in the X direction, okay, we're going from right, so 21.3 minus 18. So it's 3.3 inches from C to D. I'll write that down over here. Oops. 21.3 inches minus 18 inches. 3.3 inches. Okay? So let me go ahead and put that in here, 3.3 inches. What else might be helpful? Yeah, how high is it from point C to point D? Okay, and it gets a little crowded in there, as it often does, but I'll show this right here. All right, so LCD Y just ends up being 7.1 inches minus 4.7 inches. $2.4. All right, are we there? Is there anything else that we need to know on this diagram? There's a glaring hole still. We have not established the direction of FBC. Okay, so that's our last thing we need to do here, is to come up with, for this line of action for FBC, what is the slope? All right, how do I do that? Okay, right, so it has to have the same geometry to it, same slope to it as the slope of the physical muscle between B and C. All right, so if I take like BY, or you know, the height between B and C in the Y direction, and put that on the vertical over there, and the horizontal distance from B to C, and put it on the horizontal, then that gives me a slope. Okay, so let me do that. From B to C, horizontally, we've got essentially 18 minus 16.1. Okay, and I'll go ahead and put that in here. Oops. So 1.9. And what about the vertical direction? Okay, 8.5 minus 4.7, right? Which gives me 3.8. So 8.5 minus 4.7, and that would be 3.8. Okay? So now I have the direction of FBC. Do I need anything else on my free body diagram? I feel like we're in good shape. What now? Yeah, so we need to do a sum of moments around point D. This is what someone suggested right at the very beginning. This is what we're trying to do. We just had a little bit of work to do before we got to that, right? So now it's easy though, because everything is on our diagram, right? There's nothing that we don't, or nothing that we need that we don't have on the diagram already. So where do you want to start? Okay, we'll start at point A. That one's probably the easiest. Counterclockwise, it looks like, since we have a force that would tend to try to rotate this thing that direction around point D. So I have positive 130 pounds multiplied by what? 22.45 inches. Then what? Okay. We need to have that FBC. It basically is going to break into two components, right? One that goes upward and one that goes to the left. Agree? Which one do you want to deal with first? Okay, the horizontal piece first. What direction does that tend to try to rotate around D? The horizontal piece only. Clockwise, right? It's going to try to go clockwise around point D. Okay, so I put minus FBC. I don't want the entire FBC. I want just what? Just the x component. To get that, I take 1.9 over the square root of 1.9 squared plus what? 3.8 squared. Now what do I multiply this by to get a moment? Because so far that much is the x component. I need to multiply it by, right, 2.4 is how far the line of action is from that component of the force relative to point D. So I put 2.4. Okay, now what? Now I need to deal with the y direction. Tendency of that is to rotate what direction around D? Clockwise, which again is going to be counted as a negative. So negative FBC, and again, I don't want the entire FBC. I want just the vertical component, right? So to get just the vertical component, I multiply this by 3.8 over the square root of 1.9 squared plus 3.8 squared. And I take that and multiply it by what length? 3.3 inches is how far it is from that line of action to point D. All right. Do I have any other forces that would tend to create moments around point D? I think that's it. So we can set that now equal to 0. Can we solve it? Yeah, we only have one variable in here, right? FBC is the only unknown that we have to solve for. And so we could do a lot of manipulation manually to kind of factor that out and deal with it that way. Or we can, we can thank the maker of free body diagrams that we have a calculator at our disposal that can do this kind of thing. So let's go ahead and put this equation directly into the calculator. All right, 130 times 22.45 minus, instead of putting in FBC, you just put in X to account for that variable. Do this times 1.9, and I'll go ahead and I'll multiply also by the 2.4 while I'm here. And then I divide this by the square root of 1.9 squared plus 3.8 squared. Okay? And that takes care of that first term, or that first term that has an unknown in it, second term overall. All right, then what? Okay, minus X times 3.8 times 3.3 divided by the square root of 1.9 squared plus 3.8 squared. Okay, at this point it's tempting to hit the equal sign, but you don't want to do that. What do you want to do? Alpha equals actually puts in the equal sign as a symbol, and then you put 0 at the end. Now that I've got that whole equation in there, the next step is to hit Shift, and above the Calc key there you see Solve. Solve for X. It ends up giving you 725.1. So FBC 725.1, and that would be in what units? So what's the answer? I. And that wasn't that painful a problem, actually, right? It's just, it was a complicated figure that has some, different way of communicating information to you, but nothing that you're unfamiliar with. Sound good? Awesome.